Let's explore database streaming and real-time analytics. Modern applications require immediate insights and quick responses, making it essential to process continuous data flows in real time. Let's compare stream processing with batch processing. In batch processing, data is processed in large chunks at scheduled intervals, which leads to high latency and high throughput. It involves scheduled execution and is suitable for complex aggregations. Stream processing, on the other hand, processes data continuously as it arrives, offering low latency and real-time capabilities. It involves continuous execution and event-driven responses. Let's explore the key components of streaming systems. First, we have data sources like applications, sensors, logs, and external application programming interfaces generating continuous data streams. Next are the stream processors, which are engines that transform, filter, and aggregate data in real time. Then comes the storage layer, which includes fast databases and caches for immediate data access and persistence. Finally, we have the analytics engine, which provides real-time dashboards and alerting systems for instant insights. Now let's explore some popular streaming technologies. Message brokers like Apache Kafka, which is a high-throughput distributed streaming platform, and Apache Pulsar, which is a cloud-native messaging and streaming platform. For stream processing, we have engines like Apache Flink, a low-latency stream processing framework, and Apache Spark, a unified analytics engine with streaming capabilities. Let's break down the stream processing architecture. It starts with a data source, which could be events, logs, or sensor data. Then data flows to a stream processor, where it's transformed, filtered, and aggregated. Finally, the processed data arrives at a data sink, such as a database, dashboard, or alerting system. Here is the basic stream processing flow. Stream is equal to source.readStream. Filtered is equal to stream.filter applying a lambda function, where x.value is greater than a threshold. Aggregated is equal to filtered.group by key, and calculating the sum of the value. Finally, we write the aggregated results using writeStream.start. Let's discuss windowing concepts in stream processing. First, we have tumbling windows, which are fixed size, non-overlapping time intervals. For example, data could be processed every 5 minutes in intervals such as 10 o'clock to 10 minutes past 10, then 10 minutes past 10 to 20 minutes past 10, and so on. Next are sliding windows, which are fixed-size windows that overlap with regular intervals. For example, a 5-minute window sliding every 1 minute, allowing for overlapping analysis. Then there are session windows, which are dynamic windows based on periods of activity. An example is user sessions with 30-minute timeout gaps. Lastly, there are global windows where all events are aggregated into a single, unbounded window and continuously aggregate until a trigger fires. Let's dive into some real-time analytics patterns. Common patterns include event detection and alerting, real-time dashboards, stream enrichment, and continuous aggregation. Here's an event detection example. We define a function called detectAnomaly that takes a stream as input. It returns a stream that filters events where the value is greater than a set threshold, and then maps those events to create alerts. Let's talk about data consistency and delivery guarantees in streaming systems. There's at most once delivery, where messages may be lost but never duplicated. This offers fast, low-latency processing but has potential for data loss. There's at least once delivery, where messages are never lost but may be duplicated. This provides reliable delivery, but requires duplicate handling. Then there's exactly once delivery, where each message is processed exactly one time, offering perfect consistency but increasing complexity. Lastly, there's best effort delivery, where no delivery guarantees are made for maximum speed, which means the highest performance but minimal reliability. Let's explore real-world use cases and applications of database streaming. In financial services, streaming is used for fraud detection, risk analytics, and trading systems. In Internet of Things and sensor networks, it's applied to sensor monitoring, fleet tracking, and industrial analytics. In e-commerce, it helps with user behavior analysis, recommendations, and inventory management. For system monitoring, it is used for performance metrics, alert management, and log analysis. Let's consider the challenges and best practices in database streaming. Key challenges include managing late arriving data, handling back pressure, state management, and monitoring and debugging. Some best practices are designing for item potency, implementing proper monitoring, planning for failure recovery, and optimizing for throughput. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.